and welcome to Compounding Curiosity. I'm your host Kalani Scarrett, and this podcast is all about compounding your curiosity alongside my own through thoughtful interviews with interesting guests. For transcripts and detailed show notes, check out the links in the description. Hopefully you're as keen as me to learn something new, so let's get stuck in. Okay, how are we? My very special guest today is John from Asianometry, creator of the hugely popular Asianometry YouTube channel, where he posts video essays on business, economics, and history within Asia. But in today's conversation, we cover EUV lithography, ASML, and everything in between, from how it all works to the impact on the world and what it all means. So, an extremely valuable and important conversation, and one I'm extremely proud of and happy to share with you. So please enjoy my conversation with John from Asianometry. Oh boy. John, thank you so much for coming on today. A big topic, very in-depth. You might need to hold my hand a little bit, but we'll start broadly, start easy, maybe just with EUV, and then we'll get deeper in the weeds on the technology and then ASML. So broadly, do you just want to talk about what is EUV lithography? How does it work? Why is it important? And cheers for coming on too.
Yeah. I'm glad to be back on for the third time to Compounding Curiosity. Let's start with kind of discussing why EUV matters, right? EUV is the continuation of a lithography trend that's been going on for half a century, I would say. So in the 1960s, when we printed semiconductors, we used essentially screen printing techniques. This was basically what you would use to print anything, really. You started with the drawing of your chip design, right? It'd be hand-drawn, and then you'd carve it onto this red tape called Rubylith. And you'd be standing on, actually you wouldn't be using like sharp shoes or anything, you actually use your socks and just cut this up yourself. The finished product was called an artwork, and you use that to create a photo mask. The photo mask is shrunk down 10 times using a special camera, and then it's printed onto the wafer using something called it kind of looks like a photocopier, I would say. And this photocopier uses light to transfer the chip design pattern on the photo mask onto the wafer. So we coat the wafer using something called a photoresist, and that's a special chemical that reacts to the light coming to the machine. And the machine that actually flashes the light is called your exposure tool. And so back then, when we had contact printing, it really is kind of imagined like a photocopier. You press the mask hard against the wafer, and then you flash it with light. And the resist is left with like the imprint of the chip design. And back then, we could flash the whole wafer at a time, which is just called the mask. Nowadays, you have a little more subtle changes, which we'll talk about later. Now we can use this kind of, flashed photoresist in the wafer as your stencil for etching processes down the line. This is where we actually etch the design permanently into the wafer substrate. So those were the basic early principles of lithography. That was the 1960s. That was like 60 years ago. That's crazy. And so people found was that when you got smaller and smaller designs, you wanted to get smaller and smaller wavelengths, right? If you think about it as like a chisel, right? If you want to chisel and etch lines that are an inch thick, it's harder to do that if your chisel is 2 inches thick. We want a smaller chisel. So, back in 1980, we had something called 435 nanometer wavelengths, mercury arc G-line lamps. And that was fine because the leading edge process node in 1980 was 1.5 micrometers or 1,500 nanometers. So you can see 1,500 nanometers with a 435 nanometer chisel, super easy. But Moore's law meant that the industry kept shrinking the nodes, right? And the feature sizes they had to etch at. So from 1987 to 1999, leading edge went from 800 nanometers to 180 nanometers. And 435 nanometers no longer was good enough, so they switched to eye-line lamps, which is eye-line referring to a type of light. And that light had a 365 nanometer wavelength. But, Moore's law kept going and kept going. So by 1999, they switched to 248 nanometer krypton fluorine lasers for the 180 nanometer process, which is leading edge at the time. 2 years later, they switch again to 248 to 193 argon fluoride. So, they all thought about what was going to happen after this because, the Moore's law meant that the process nodes kept getting smaller and smaller and smaller, and you're running out of wavelengths. So they thought about going to a more disruptive type of lithography, which, at first it was, they've looked at a variety, which we'll talk about later. And then they said one of the first ones they looked at like 157 nanometer, which is kind of like a bridge. And then finally, they decide to do immersion lithography, where they send 193 nanometer light through pure water. But ultimately, what was the end goal that people wanted to do? They wanted to go from 193 to 13.5. So essentially X-rays. And that's what EUV is. It is essentially the continuation of this kind of 60-year lithography trend, where it's the smallest possible chisel they can possibly have.
And the jump from DUV to EUV, was that an extreme jump, or?
It was a pretty extreme jump, I would say. There's a lot of engineering, because all the principles that, while the overarching principle of EUV remains the same, you're using light to make designs on a wafer, the mechanism through which you generate and focus and bring that light to the wafer changed a lot.
And the margins for error are incredibly small with all this as well, because since we're working in, such tiny details.
Yeah, that's always the case, but particularly, yes, with EUV. It's fun stuff.
Scary stuff for me, trying to get my head around it. And listening to you, it's like, oh my God, I'm just trying to keep up, but it's so cool. So you want to quickly explain and give a brief overview of who ASML is now, and then why they're so important in the whole factor of the world, I guess.
ASML is a kind of a joint venture company that exists after. They're a joint venture of ASM and used to be like a unit of Philips. And so they struggled through the 70s and 80s because they were going against the Japanese lithography companies, right? So the Japanese lithography companies, Nikon, Canon, had really dominated the American semiconductor manufacturing lithography providers. They were, for reasons really tied into process, tied into overinvestment in the space, and also their own technical competency. So ASML came up in a time when they were competing against Nikon, Canon, and one of the reasons that they became leaders in the lithography field was that they jumped onto what I called before 193i nanometer light. And they were one of the first companies to bring that to the market. They brought it faster than Canon and Nikon. And all this other time, they were also developing EUV as well. But one of the reasons why they kind of surged forward and became what I would say a leader in lithography was 193 immersion.
And do ASML, is this right, they are the only supplier of EUV machines?
They are the only commercial supplier of EUV machines, correct. They're not the only ones that have tried to make it.
Do you see other companies being able to make it as well? Or how big is that jump for them as well?
That's an interesting question. I think it's like, we can discuss. Like, we'll talk a little bit about how EUV developed as a technology and why ASML came into play. So like EUV itself, the technology, the notion of using essentially X-rays to develop a chip pattern was demonstrated in 1986, and it was actually demonstrated in Japan at a telecom company, NTT, their R&D lab, right? And the Department of Energy they reads this document, and they're always looking for kind of the next generation lithography technology. Department of Energy funds a team to get some basic stuff to fiddle with to get a tool working, right? And at this time, EUV was just one of many next generation lithography technologies. You have electron beam direct write, proximity X-ray, 157, as I mentioned. So all those other things. So EUV wasn't particularly well reviewed, I would say. In 1997, Intel comes along. They see this new EUV tech and they like it. And they forward some funding, like $60 million or something, to keep the team together. And then they work together with the rest of the American semiconductor manufacturers to create EUV LLC, a consortium to fund the basic technology work. So they get around 80% of the work done. There's a tool, they have procedures, they know how to do it, but the 20%, they leave the other 20% to the industry. Of course, the last 20% is the hardest part. So ASML had joined EUV LLC with American permission because they acquired a company called Silicon Valley Group Lithography. And like I said, there was no American lithography companies at the time because the Japanese basically wiped the floor with the industry in the 80s. But Japan actually was also in the picture. Nikon and Canon were not allowed to join EUV LLC because of geopolitics and competition at the time, but they were allowed to attend the meetings, they were allowed to receive information, and they were very sophisticated themselves. I mean, they had a lot of government funding. So, for a few years and into the 2000s, ASML and Nikon and Canon were all competing to build the first viable EUV machine. And I think at the end, after the global financial crisis, basically Intel chose ASML like ASML solution, Canon dropped out pretty quickly, but Nikon kind of moved on. And they actually had developed a working test tool, a completely finished, or not completely finished, but it was a tool that worked. There were some significant issues with it, but it worked. And it was probably the most sophisticated lithography tool in Asia. But, after the global financial crisis, Intel decided to choose one. They went with ASML, and then Nikon dropped their product. All in all, I would say Nikon and Canon and Japan in general, spent about 10 to 15 years on their own product. I would say 10 years, more like 10 years. And they invested something like $5 to 10 billion. I estimated it'd probably take probably about 15 years for a company to go from scratch to an EUV machine that's probably workable, and something in the lines of $10 billion.
Wow. And that's what I mean. It might not even be financially viable to make it worth it, all that time and effort.
Correct. And that was one of the issues that caused Nikon to drop it. No one else would use this machine.
Wow. Okay, let's talk about the insanity of the machine. So given how important ASL machines are, yet they can only make 50 high-end EUV machines per year. So could you talk about the insanity that is the $150 million lithography machines, and what makes them so expensive, I guess?
They are very over-engineered. And part of the reasons why they're so over-engineered is because they were supposed to hit a certain process node back in, I would say, the mid-2000s. But that changed as they came across issues with defectivity, with the issues with the light source and whatnot. And then as this kept pushing, what happened was the process node that EUV needed to enter into kept getting higher and higher. So EUV eventually hit at 7 nanometer. That basically requires a very powerful light source. And so part of the reason why EUV machines are so crazy over-engineered is because they have to generate so much power. And the reason why they're so expensive is because ASML has been working on them for several decades. There's all that depreciation costs they have to pay for, but also that they're incredibly energy hungry. It's estimated that one EUV machine uses as much energy as 10 DUV machines. Yeah, TSMC has a N1 fab that they're doing in Longtan, Taoyuan, and that single fab is estimated to use as much energy as the entire country of Costa Rica. And 1 year of operations will light up the Eiffel Tower for 17,000 years. So that's part of the reason why these machines not only cost so much to build, but also cost so much to run.
And we haven't even talked about setting up and logistics. So in your TSMC deep dive last year with me, you said a lot of people just kind of imagine the EUV machine coming in like an Amazon box. You pull it out, it's ready to go. But the reality is there's a bunch of modules that the TSMC and the foundry chooses the module and puts it together how they imagine, how it may best work in particular. So, what are some of the logistics behind installing an EUV machine? You can't just buy it. Yeah.
It's kind of crazy. I mean, I think a lot of people ask me this, like, why is it so... like about the difficulties are always bringing it. And I've asked multiple people this, including people who work at ASML. And unfortunately, it's not as exciting. I mean, they break it down into parts and they fly it over. So it's not like that time UPS shipped like a whale shark to the Georgia Aquarium. So it's like, in this case, this EUV machine, once it arrives, they truck it in and they install it. I mean, I wish I could say something more exciting than that. It's disappointing to a lot of people when they hear it.
There are a few engineers and stuff that hang around and make sure the setup's right. Is that right?
Yeah. I think ASML has... Actually, when I was there at TSMC's Tainan in the south, basically you see, TSMC's fabs, UMC's fabs, all that other. And then you see kind of all their suppliers too. You have Applied Materials. They have a very large facility there. ASML is one of their larger R&D locations is actually in Taiwan, and they're in one big building in Tainan too. It's really interesting how kind of they actually have to kind of build there to get things going.
Yeah, and on the topic of suppliers, I saw in your video you mentioned that ASML is kind of like a Boeing or an Airbus in that they collect a lot of different suppliers to make their parts and don't do it in-house. So with ASML being extremely important to TSMC, but there's also important companies to ASML like Carl Zeiss, Cyma, Trumpf, if I've got all those names right. But who are the important suppliers to ASML and why? And do you want to talk about the supply aspect of it?
I think Carl Zeiss is probably the most well-known one. I think the interesting thing is Carl Zeiss actually has a joint venture with ASML. So it kind of emphasized, when I was working on that video, I was thinking a lot about how much that ASML really focuses on owning the certain parts of the technology that are critical to them, right? When Cymer, their laser provider, kind of reached certain requirements, they acquired the whole company. But at the same time, the company is like Boeing in that they want to sit at the very top. They want to own all the value, right? And when they don't really let and get themselves in a situation, in my opinion, that they want to, where they're going to allow themselves to be leveraged by a supplier. Otherwise, they'll acquire that company. Really, if you think about what's kind of the most important parts of, if you think about what makes the EUV bring its value, right? You think about the different parts of it, a lot of that is already owned or partially owned by ASML. If you think about it, you have to break it down. You have the mechanics, the machines, the mechanics moving the wafers parts. You have the light source. You have the optics. You have the photoresist, which I think actually is not provided by ASML. And I think that's it. But so I think all of those are very, very closely controlled by ASML. So in general, what I'm telling you is that, they have a lot of suppliers, and the ones that are very important, you tend to have already called out.
Okay, yeah, fair enough. And with the power, given that ASML are the only company that makes EUV machines, and they're used by all major global semiconductor chip manufacturers, so like the layman might ask, the layman being me, why does ASML not seek vertical integration? So in the sense of competing against TSMC and the like. So I think some people may wonder if ASML has a monopoly on EUV machines, what stops them from competing in the fabrication space?
I think the big thing to point out is that TSMC has been doing fabrication for 30 plus years. Samsung is backed by an immense chaebol. And I would say that just because lithography is the most charismatic, it's the most popular part, it's the one everyone thinks about with semiconductor manufacturing, it's not the only one. There's other things like etching, deposition, packaging, testing, whatnot. All those parts have to be integrated into the clean room when TSMC makes those chips. So the expertise TSMC brings to the table is not to how to build like a complicated lithography machine, and ASML wouldn't be good at that either. I would say wouldn't be good at kind of putting all that part. Just the same way as TSMC doesn't know how to build a machine, ASML doesn't know how to use that machine along with all the other machines that need to be used to make a full chip. And I also think, it's unlikely that ASML will make their money back if they're not selling to other clients, right? If they decide to go and compete with their own customers, they're not going to make their money back. They need to sell to like a Samsung. They need to sell to Intel. They need to sell to TSMC. And that was one of the geopolitical risks for ASML. Like, they needed to pay this incredible investment back. And they might have made a lot of that back if they were able to sell to SMIC, to Hua Hong, and all those other companies. So that was something that wasn't allowed to them by American laws.
Perfect tie-in for the next question. So with the trend of de-globalization and supply chain security, are they a threat to ASML's asset-light model, which uses the ton of suppliers?
I actually looked into this, and I believe like over nearly 50% of ASML suppliers are within the EU. So large portion of ASML's supply chain is pretty localized. De-globalization is something that I think every company in the semiconductor industry is trying to practice. They're trying to bring more of that in-house. I think they're good. I think they're going about it the way that they're best going about it. I think it works. I think it works for them.
No, fair enough. And sorry, I'm jumping around questions here because my mind jumps around as well. But I picked up in one of your videos. Could you just explain why zero defectivity is one of EUV lithography's key challenges to overcome?
It was when people were kind of going through the zero defectivity or the various problems, the deal breakers to what would make EUV lithography a real thing. Zero defectivity was kind of the biggest ones, right? The problem was that defects on the mask are very significant. They have a huge impact. So if you have one problem, so if you think about back to the stencil, right? That photocopier where you're trying to make a bunch of wafers. If you have a problem with your stencil, with your design on your mask, and you print wafers, like tens of thousands of wafers, it could be actually a long time before you discover that there was a problem on the chip. Could be when the chip when you run the test on the chip doesn't perform well, and you have no idea why that came out, like why it came out that way. And it's a huge problem because then suddenly you've wasted tens of thousands of dollars or tens of thousands of wafers, which means millions of dollars, and now you're in a huge problem. So one of the biggest problems with when they were trying to build what EUV was how to prevent those defects from ever happening, and also making sure, and it's even more challenging because with EUV, that mask, that photo mask, the reticle, is not transmissive, meaning that light is not going through it. Light reflects off of it. And if you know kind of how mirrors work, that means every line, every part of that mask design on that has to be perfect. So that's just one part of it, right? So producing the mask, making sure there's no bumps, there's no kind of defects on the blank itself. That's number one. And then number two, you have a situation where you have to prevent particles from landing on the mask and interfering with the light on the exposure process, which is doubly difficult because you don't have any, early on, you didn't have any protections from keeping particles getting into that EUV machine. So you had to kind of zero out the whole thing, go into as good of a vacuum as you possibly can. And that has a significant amount of cost. And so eventually they got to create what they call the pellicles. I think they use carbon nanotubes, as far as I know, which is crazy. It's crazy that they found a material that actually allows UV light through, and not only has to let UV light through once, but twice without absorbing too much of that light. So it has to go through one time before it hits the mirror, and then after it hits the mirror. So that was one of the bigger significant issues. And with creating those blanks, and it was a process that could not start until they had a tool to actually test it. And then from then it took, I would say, multiple years for them to finally reach acceptable levels.
Yeah, it's just crazy. Because I was reading as well, the flatness in EUV machine mirrors are just insane. So the mirrors are polished to a smoothness of less than 1 atom's thickness. So to put it into perspective, if the mirrors were the size of Germany, the tallest mountain would be 1 millimeter high. Is that true? Like, what is it? Explain this to me. Explain the magic.
It's crazy. These mirrors are insane. And the reason was because, like, virtually every material that could have been used does not let 13.5 nanometer wavelength light through. So, like I said, there's no transmissive materials in an EUV machine. It's all reflective. So when they moved to reflective optics, it was a totally different paradigm. And each mirror it's kind of crazy how these mirrors are made. Like they have 50 pairs of molybdenum and silicon, and each each layer pair by itself is 7 nanometers thick. They're grown. Actually, I would say the way they're grown is actually not that surprising, or not that surprising. They use deposition, and so they basically grow these things. It kind of reminded me how they use similar vapor deposition procedures to make synthetic diamonds, which is fun. So basically, the whole point is that they want to make sure that you preserve as much of the light as possible when you bounce off the mirror. And even so, even if the mirror is made perfectly, you only reflect 70% of the light at its maximum.
Wow. God. Because, yeah, even the same thing I saw in your video, even the size of a virus can cause problems down the line. Like, something so minuscule just ruins a whole batch. Unreal. And on the economic side of it, are we even able to build a simpler, cheaper EUV machine?
I think it's a good question. I think we can build like a tiny, fun science project pretty easily. I think the question is whether you can use that project to create tens of thousands of N3 or N5 wafers in an industrial setting, right? One of the reasons why EUV kind of took so long was because of the power source, like I mentioned. So I think like you could have inserted it into the 90 nanometer process node like it was originally asked for. But at that time, I would doubt such a device would be economically viable against like a $5 million DUV 193 machine. So I think like that was one of the big problems, was that EUV, when you run it through a process node, the process node is nothing more than a manufacturing line, right? So when you run it through that process node, you're not only using EUV machines, you're EUV exposures or EUV layers. So there's a lot of DUV 193 immersion systems still in there, and they're used because they're workhorses. They're very reliable. And I don't see EUV ever getting to a point where they replace DUV machines, where they would rather use an EUV machine if they didn't have to. Does that make sense?
Yeah. And if I'm right, as you go to newer nodes, so DUV obviously can produce a lot quicker and more than an EUV machine. Is that right as well?
Yep, the throughput's higher.
Yeah. If it gets harder and harder, how do you even combat that?
And you don't have to have all these restrictive maintenance, right? Like EUV is a very delicate, the whole thing barely works, I would say. It works pretty well, but it barely works. So a DUV machine, I think, is far more effective.
And with EUV, it was such a joint collaboration. It was such a mammoth feat to even be able to get there in the first place. What the hell's next? How do we go to take that next step?
I was reading an article with like the ASML CEO, or maybe it was the CTO or something, but they were talking about what they were trying to deliver. They're trying to deliver high NA EUV, right? Which is where you raise the numerical aperture of the EUV machine so that it collects more light and you can get a smaller critical dimension. But what is after that, right? And there's something called hyper NA. So hyper NA is kind of like how immersion lithography raised the NA of the 193 nanometer light, right? To make it to improve the critical dimension even more, right? So that would be the theoretical next step of EUV, right? Because I don't think they're going to move away from that wavelength light anytime soon. The only problem was that the high NA EUV machines are already incredibly expensive. They're $300 million, right? Or something like that. And so that's like what? How many companies are going to buy a high NA EUV machine? Like $300 million in their pocket. So what's next? I don't think that's how the semiconductor industry works. They know what we'll do in the next 5 years, but anything after that, like they have no clue. They have to look into it, and they're kind of feeling their way through the river. They're making their way across the river by feeling the stones on the bottom. So I think they are very poor at making predictions after 5 years. We don't know. We don't know what will be next. There could be other things, like what are they using to etch the masks themselves? You can basically use electron beams to write at feature sizes even smaller what EUV can do. But the difference that makes EUV more effective than technologies is that you can still use EUV to get the scale, right? You can you can still step and scan across the whole wafer to do many designs exposures at the same time. It's kind of like, you're still printing as opposed to handwriting a signature, right? If you're handwriting every signature every time, that's going to get tiring, where if you just stamp the signature over and over again.
And defects too, I'd assume, would be better?
Defects are always a problem.
So this was a question submitted. I have to give credit in the show notes because I don't have it written down who it's from, but what kind of threat is the emergence of 3D DRAM that places more emphasis on etching and other processes rather than lithography?
I need to talk about this DRAM thing for a second, because everyone keeps complaining to me, John, you don't know how to speak DRAM, it's DRAM. And the only thing I have to say is that, first, my father said DRAM. So I grew up thinking it was DRAM. I did my first videos about it. And then people started yelling at me, like really angrily. I get emails just saying, like, I like your videos, but I cannot accept the way you say DRAM. You don't know how it's pronounced. I know how it's pronounced, but I can't lose face and change it. I have a face. It's Asian culture. Y'all got to understand. You got to save face. Anyways, so 3D memory has been around for a while, right? Actually, so the technology has been around. So we've had 3D DRAM, we've had 3D image sensors. That's been around. Only recently have we been able to achieve like true 3D integration on logic chips using what are called through silicon vias, TSVs. Is this a threat to lithography? In a way, yes. I do agree that has a risk of kind of taking away some of the supremacy that lithography has within the manufacturing chain, right? Because lithography has sort of kind of petered out after 50, 60 years, you're going to see a possible de-emphasis on lithography and more emphasis on other parts of the manufacturing process, like etching, like deposition, but also packaging as well. I think that's, it's a challenge for ASML because they've staked a whole lot on lithography, right? And, they've sucked out a lot of the investment of that industry. And if they cannot continue to bring down more economically viable lithography machines down the line, that money, that investment still needs to go somewhere. And so you're starting to see, you have situation when you see something like TSMC and they're doing a lot of their advanced packaging in-house, right? That's interesting. You look at that and that's kind of a situation where it's kind of like when you start seeing your best customers kind of buying other products. So, but at the same time, like I said before, it's hard to see what's coming down the line like 5 years from now. So there is a future where you see a lot of investment in all these other parts of technology where lithography basically stagnates, where we just see incremental improvement on certain aspects. And that's hard because you're not going to have those replacement cycles going through.
On the topic of emails, people complaining about your pronunciation, but also in our last deep dive, you mentioned ASML employees often email you. So I'm just curious, what's the common reason for why they email you?
They're very nice people. They're very nice people. I think TSMC is just more closed. ASML is a lot more open culture. I think they're more open to it. And TSMC, they're very closed. And they also speak Chinese too. So, I mean, most of them don't watch the videos anyways. They're very nice people. I really enjoy them. And I think they have a lot. They're not only really passionate about what they do, they have incredible pride because they're working what is now one of Europe's most prestigious manufacturing companies. It's basically the only manufacturing company other than perhaps Airbus in the top 100. So, I mean, people have a lot of pride over them.
Yeah, even just reading through a lot of your YouTube comments for research for this video, it is so helpful and people are so keen to share their thoughts and their experiences. You've got a good group of fans sometimes.
Yeah, they're nice. A lot of them are nice. The mean ones are quite mean.
But yeah, so obviously with all your notes, anything else we haven't covered that's consequential about the future of ASML and EUV, in your opinion?
No, I think we've covered a lot in a very short amount of time. I think it's very interesting to see. I want to learn more about Hyper NA EUV down the line. And I also really be curious to know about, in the future, what can they do to fix this power consumption problem? Because this power consumption of these EUV machines is basically makes EUV unacceptable for a vast number of companies, right? 6% of Taiwan's entire energy consumption is basically to TSMC, a single company. And that goes up higher every time they buy a new EUV machine, right? I'm very curious, and I think a lot about what can ASML do to reduce the power consumption on these machines, especially when you get to even more advanced products. And what consequences will that have for the chips themselves too? That's more of a TSMC thing, but it is very curious to me. I see that as one of the big problems with semiconductor manufacturing and its environmental impact.
I still remember you talking about water consumption at TSMC, and I thought that was so interesting, and the problem there and how they solve it, and just the science behind it.
Actually, when I was during my visit, I noticed that in southern Taiwan, I noticed that they're carving out a canal that would bring water from the ocean, or from a reclamation plant near the ocean, and they're bringing that to a massive reservoir. There's not just one massive reservoir, there's multiple around these fabs. It's literally sitting next to the fab. It's kind of like some nature area, but it's a huge lake. And they're doing some incredible water projects down there. And I think that's something to the water consumption. Of course, everyone talks about that. It's a big problem, especially in Arizona. It's curious to see how they're tackling it in Tainan, because it's just amazing. Just visiting these plants is amazing.
Because it's like a whole little compound complex, kind of hard to even imagine. Mini city, isn't it?
It's a city. It's basically a small city, because that fab. So there's Fab 14, Fab 18. Those are the two big ones, and Fab 18, which I visited, and it will take a good maybe 2 to 3 minutes to scooter around that, and it takes 30 to 40 minutes to walk around it. And they're building phase 7, and when I was there, they have 4 projects going on, multiples. It's crazy. And they're bringing in, they're probably going to fill these things with some of these crazy EUV machines too. It boggles the mind, just the infrastructure, not just on the water side, but the electricity side that is necessary to make this single fab work.
Bloody smart humans behind all this. I love hearing about stuff like this. But I'm curious about your take on this, given your knowledge, insight. But does it worry you, or how do you think about how much of the world economy is dependent on so few companies?
I've heard a lot about this. So this is the first time I'm probably going to say this anywhere. But I think I don't think the world economy is that, as the world economy right now is dependent on advanced semiconductors, right? Advanced semiconductors are sort of, to the technology, to the rest of the economy, and to policymakers, they're seen as like, they're almost like a pathway to a better future in some way. It's like your option for a better future. In reality, what I've noticed is that the majority of semiconductors that actually run your life are very small, are very old, very small, and very just normal. There are 200 fabs around this world, and many of them, I think, are of those types. You don't really notice them. They're quite small, and like they just churn out, and they make money. They probably make good money, and they just run until someone tells them no one buys their output anymore. I think most people will never use an N2, or I guess a lot of people will actually. A lot of people will use these chips because they're going in smartphones. But other than that, like, a lot of people are not going to really see their lives change because of an N5 or N3 chip as compared to some of these other chips. I like to think of these chips are like bodybuilders, right? They're optimized for one thing, and they're not really survivable in the real world. So I hesitate when people say like the world economy is dependent on so few companies. There are a lot of other companies that are much more important to the world economy, I would say. You know, like your energy companies or your food companies or logistics companies or something like that. So I think it's just, you know, it's still kind of weird for me to think about it. Maybe I'm wrong. I think there'll be plenty of people emailing me saying like, you know, John, advanced semiconductors are the only way we can we can go to Mars or something, or like find the future, but I generally don't agree with that.
Yeah, no, it's fair enough, because I'm a noob talking about this, but reading Chip War, hearing you, it does seem like we've reached a luxury point, whereas before it was better chips for a better military. You know what I mean? There's a bit more on the line, it felt. I don't know. That's just my takeaway so far.
It's kind of curious, because I was like, you know, I'm doing video about kind of why Europe lost in the semiconductor, why they fell behind in the semiconductor industry. And one of the big reasons, or very early on, one of the things that happened is that, you know, they decided to de-emphasize work on semiconductors to build nuclear. To build weapons, essentially. To build the biggest weapons. And I think it's kind of interesting to see that kind of certain policy choices made by countries at certain times had kind of big reverberations down the future.
Just like chip manufacturing, I guess. One small little defect amplifies out. So honestly, cheers a million for coming on today. Like, at the start there, I was almost in tears. I was like, this is the greatest day of my life. It's like watching a genius at work. I genuinely mean it. It was freaking insane. So yeah, thank you so much. Anything you want to plug, I'll link all your videos, your playlist, ASML playlist. Yeah, anything else?
Oh my gosh. No, this thing is good. Thanks for taking the time on short notice, by the way. It's because we're trying to make this recording before I come down with COVID. So I really appreciate it. And you know, watch the Asianometry channel, everyone, and feel free to email me if you want to say hi.
Perfect. Always more than welcome. If you enjoyed this podcast episode, be sure to check out the website compoundingpodcast.com. On the website, you'll find every episode complete with transcripts, show notes, and other related resources. If you want an email notification every time an episode releases, plus my lessons and takeaways from each episode, be sure to sign up to the Substack. So that's compoundingcuriosity.substack.com. Either way, links to all content mentioned today will be in the description below, and you can also connect with me on Twitter @ScarrettKalani. But until next time, have a good one.